This curve maps standard expectations for effect sizes in educational research. Shifting a student competency metric by a Cohen's d of 0.8 is usually considered highly successful. A 2026 study recorded a result well outside these standard parameters, an effect size of 6.97. This research, conducted at Nakhon Si Thammarat Rajabat University, focused on a specific cohort, pre-service physics teachers. Table 2 shows the raw data driving this shift, the cohort's design thinking scores before and after the new instructional model. The pretest mean of 13.10 increased to 35.15. A t-value of 43.55 confirms the strength of that massive 6.97 effect size. Traditional physics pedagogy often relies on theoretical transmission, where students memorize abstract equations. This approach frequently fails to develop practical engineering skills. This study shows that shifting the focus from rote recall to applied competency significantly increases the cohort's ability to translate theoretical physics into physical design. To understand why this change occurred at such a scale, we have to deconstruct the specific architecture of the instructional matrix the researchers deployed. Before building the intervention, the researchers ran a diagnostic on the pre-service teachers to identify their exact instructional deficits. This table breaks down the results of a 20-item needs assessment, mapping exactly where the students felt most deficient in their training. The highest need identified was in prototyping. The students reported a 4.41 mean requirement for hands-on engineering design instruction. The data reveals a clear gap. These teachers could handle abstract physics formulas, but they lacked the specific engineering capacity to build tangible solutions. Figure 1 outlines the framework the researchers used to bridge that gap, a deliberate fusion of STEM principles and design thinking. This framework integrates the analytical rigor of interdisciplinary STEM into a human-centered iterative design loop. Identifying this specific gap between abstract theory and physical execution provided the roadmap for an intervention capable of shifting competency at scale. To test the framework in a live classroom, the researchers used a quasi-experimental design. They mapped the curriculum onto 5 distinct stages: understand, define, ideate, prototype, and test. The classroom observation indicators in Table 3 show how the instructors executed the first 2 stages, understand and define. Rather than starting with a formula, instructors anchored physics concepts to real-life constraints found in everyday school or social environments. This approach forces students to define the engineering variables and limitations of a problem before they attempt mathematical solutions. In Step 3, ideate, the model triggers divergent thinking to ensure students explore multiple potential solutions. These collaborative brainstorming sessions require the students to develop various physical solutions for a single theoretical physics problem. The observation data noted that students engaged in active discussion, defending their diverse solutions against peer feedback. By completing these first 3 steps, the students shifted from passive reception to treating physics as an open-ended analytical design challenge. Step 4, prototype, is the phase where interdisciplinary STEM integration is physically applied. According to Indicator 1.4, physics principles had to serve as the foundation for the design of the physical prototype. The model ensures that theoretical explanations merge directly with hands-on practice. This phase provides a necessary tactile proof of the theory. Students see how a mathematical equation must account for real-world factors like friction and material limits. This transition leads to Step 5, test and reflect, which focuses on empirical iteration. The instructional model requires students to confront mechanical failure, analyze the resulting data, and refine their prototypes accordingly. Instructors mandate reflection on both the final project and the specific technical hurdles encountered during the testing cycles. This iterative transition from theory to prototype is the mechanism that produced the 6.97 effect size in design thinking competency. In the final phase, the researchers subjected the instructional model to evaluation by external pedagogical experts. Table 4 displays the model's viability within actual institutional environments. The evaluation recorded high scores for academic validity at 4.47 and process design quality at 4.19. Even a statistically effective model is of little use if it cannot be deployed within the standard constraints of a university syllabus. The highest score on the evaluation was context suitability at 4.61, indicating that this matrix is operationally ready for higher education. The study provides a mathematically validated architecture for modernizing science educator training. The data shows that the 6.97 effect size is the direct statistical outcome of this 5-step instructional matrix. These results suggest that institutions producing STEM educators should move away from purely theoretical instruction. Treating modern university classrooms as active, iterative design labs is a demonstrably effective way to develop higher-order thinking skills. By integrating STEM rigor with iterative design, the model equips future physics teachers with the specific creative and analytical competencies required for 21st-century science education.